Hello friends, welcome back to Softwaring. I'm Lord Dumal. Today I come back with another tutorial on how can you do harmonic analysis by using Ansys APDL. So as you know the drill, a harmonic load is a load which varies with time. That means it has a form of harmonic that means it has either sine or a cosine form. So it harmonically excited that body, so we call that the beam. In this case is on the vibratory state. So from the problem description, as you see from here, a 1 meter length and 0.01 by 0.01 meter cross section, that means a square cross section beam is here. So as beam is subjected to a P harmonic load, this harmonic load will change its direction like sine or cosine. That means it has a sinusoidal format. In this analysis, we try to extract the amount of amplitude at different value of different frequency level, or in this since this beam, we can measure the deflection of the beam at different frequency level. So this beam is made of structural steel. It is elasticity and Poisson ratio is given here. Besides this, you can add the density of steel, which is 7,860 kilogram per meter cube, and this beam is discretized into 50 elements. So we just discretized into 50 elements. So element division has a great impact on finite element analysis. That means when you increase the amount of element, we get somewhat accurate result. So in this illustrative example, we just use 50 as element division, and the magnitude of this harmonic is 500 Newton. So in this problem, or in this Ansys analysis, we try to see the amplitude at different frequency values. Hey, I back after a break, and this is the usual Ansys Mechanical Enterprise or Ansys APDL. So as you know, as I told you many times, APDL has no unit, so we have to homogenize every input. So we will get the output per our input. So we have to homogenize our inputs. So to start this analysis, it is usual we have to filter the necessary discipline only. So such analysis require structural discipline. So let us select structural only and proceed to the preprocessor stage. So in the preprocessor stage, we can select, as you see from in ordering, there are different preprocessor. There are different stages on the preprocessor. But every analysis may not include all the stages. So as in this harmonic analysis, we have to select the element type. So let us select our element type for this analysis. So let us select beam 2 node 188 beam element. So let us proceed to the next stage, which is by the way, such beam element type do not require constant. So let us omit it, and let us directly enter to the material properties. So from material model, it is structural linear. Since we are talking about within the linear, that means within in the linearity range. So as the material is linear, isotropic. So it is modulus of rigidity is this magnitude in Pascal, and its Poisson ratio is 0.3. And besides this, you can add the density of steel, so 7,830 kilogram per meter cube. So let us close this material more behavior and proceed to the next step, which is sectioning. So since we are analyze the beam, there is a common section of the beam. Since our beam has a square cross section, so its base is 0.01 meter or 10 millimeter, and also its height is 0.01 meter again. So if you want to see the cross section of the beam, you can click on the preview here. So this is the cross section of this beam. So it is symmetry from the origin, so there are different section preview data summary like area, the polar moment of inertia in different axes. So you can see more detailed data summary. For the time now, let us proceed by clicking on OK, and then let us start our model. So we have to create either key point or nodes. Let us create a key point for the time now. So the first key point is at the origin. Let us take at the origin, apply, and the second key point gonna be 1 meter length, since the beam has 1 meter length. So in the x1 and in the y0. So let us finished creating our key point, and then we can create lines by using key pointers. So let us create a straight line between two key pointers, and let us accept it. And then what we have to do next, we can directly enter into meshing stage. So I am the meshing from meshing size controls, manual size, lines, all lines. So the element division, as I told you before, that we consider in 50 element division. So the number of element divisions are gonna be 50, and let us accept this one and proceed to the next step, which is meshing. So let us mesh this line. Let us select all. So we get the meshed or the discretized beam with 50 element division. And then let us proceed to the next stage, which is applying loads. So before that, from the analysis setting, let us create new analysis, since we are doing harmonic analysis. So the type of analysis we do is harmonic. So let us select harmonic here, and then from analysis option, the solution method is full. Degree of freedom printout format real plus imaginary. Let us accept this one, and also we have to input the tolerance for this analysis. So let us give the tolerance as this magnitude, and then let us accept this one, and then let us define loads. So the first one is the displacement at the key points. Let us fix this key point. So let us select all degree of freedom is fixed, and then let us apply the harmonic load force from the apply structural force and moment here. Let us apply the harmonic load as this key point. So the direction is downward, so upward is positive. Let us put minus to change the direction, that is the force is a downward direction. So let us accept this one, and then once we apply the boundary condition, the next stage gonna be at the load step options. So load step options, time and frequency. Let us expand these three. So frequency and substeps. So the harmonic frequency range are gonna be 0 up to let us give 100 range, and the number of substep will be this range. So let us give 100, and a step or ramped boundary condition, we just select, we have to check the step one. So let us accept this, and after this, I think what we remain is just solve. So let us solve the current load step. Here is a status command. So as you see from the solution option, problem dimensionality is 3-dimensional. Degree of freedom is on the 6th degree of freedom. Analysis type as a harmonic. The solution method is full. You can see all detailed information about the solution option and load step options. So as the solution is done, this is good news. So after the solution is complete, we can proceed to the time history post-processing, since because we are focusing on harmonic response. So this harmonic load will vary through time. So we have to extract the time history post-processing. So let us expand this one. So as you see from here, as the time history variable. So from here, as you see this green plus sign, add data. So let us click on this. So we want this DOF solution in the Y component. So let us take this. So let us select this key point and accept this one. Now we can see, or we can extract the amplitude or the deflection at this key point, or the location of the beam where the force is applied. So from here we can see on list format. So as you see from here, at different frequency values, you can see the amplitude in the Y direction, that means in the vertical direction. And besides this, you can see the phase angle. So this is a different amplitude and phase angle value at different frequency level. Beside in list format, you can see in graph format. So let us click on here, graph data. So this is the frequency versus the amplitude of this beam under this harmonic load, or under this sinusoidal load. So as you see from here, you can observe that when the frequency is increased, that means when the frequency value is increased, the amplitude will diminish due to the high number of frequency, because as you know, in your vibration course, the amplitude and frequency are inversely related. Besides this, we can see this is just by number format, variable number format. So what if you went to in log plot? So from block control, style, and then graph. From graph, modify axes. So from here, you can change x-axis scale and y-axis scale here. So let us change the y-axis scale into logarithmic one. So let us accept this one, and if you graphed again, we can get the logarithmic amplitude versus frequency of this beam under harmonic load. So besides this, you can extract more results for the time. Now I think it is enough. If you have any ambiguous or any unclear thing related to this analysis, you can put in the comment box. For the time now, I have finished what I have. Thanks for watching. See you later.